So what I want to start with today, and we initially talked about a molecular interpretation of entropy and what it means to have these different microstates or states of similar energy. So now we want to, use that definition and use that baseline to kind of compare various systems and look at their entropy. So we're going to continue on with this topic of entropy. And I want to do a bunch of examples where we compare and contrast things and look at the smallest entropy versus the largest entropy. The biggest change in entropy that we see when we look at various substances is if we change the phase. So if we look at solids versus liquids versus gases, if we have a solid, all our atoms are in this closed packed environment. And in chapter 12, or actually the end of chapter 11, we talked about solids into detail. We're not going to go into the structure into huge detail here, but we need to know that all the atoms, and if we abbreviate them as spheres, are really close packed together. If we compare a solid to a liquid is going to be defined by its container, and the atoms themselves are separated a little bit more, and the forces of attraction aren't nearly as strong. This is going to cause them to be more randomized or more disordered, so the entropy of liquids are going to be much greater. If we continue to do this comparison with gases, gas molecules are moving really, really fast, and they're going to be spread out for each other. So if we're comparing a gas to a liquid to a solid, we're going to see the entropy of each of these increase as we go across this series. So as I draw these, the largest entropy will be drawn over on the right. Just like we were looking at the simulation, if we compared two different containers that have the same substance in it, and if our container over here on the left contains 2 moles of gas, and we compare that to a container over here on the right with 3 moles of gas, just like in that simulation, trying to keep track of all the various molecules, if we have 3 moles of gas versus 2 moles of gas, it's a lot easier to keep a smaller amount of particles. It's a lot easier to keep track of those, or it's a lot easier to order those. Okay, so as we increase the number of particles, we're going to see an increase in entropy. In some of the homework problems, you're also asked to try to determine if a particular substance has a larger molecular weight, how is that going to correspond to the entropy? So if you have a larger molecular weight, you need to keep track of more things, so it can be a lot more disordered. We can also look at something where if we have 1 mole of gas in a 1 liter container versus 1 mole of gas in a 2 liter container. In this 2 liter container, or this larger container, the gas has a lot more freedom to move around. So it's going to be a lot more random or a lot more disordered. So the larger entropy is going to be the container that's a larger size, because that gas can move around a lot more. If we look at a particular species, such as sodium chloride, as a solid versus an aqueous solution of NaCl, just like the solid to liquid to gas shows an increase in entropy, the NaCl as an aqueous solution is going to have a larger entropy than the NaCl in the solid. We can also look at temperature effects. If we have 1 mole of a gas at 25 degrees Celsius and compare that to 1 mole of a gas at 35 degrees Celsius, remember the kinetic molecular theory tells us about properties of gases. If we increase the temperature, those gas particles are going to move much more rapidly. As they move more rapidly, they're going to be more random or disordered, and it's going to be harder to keep track of them. So 1 mole of gas at 35 degrees Celsius, and we can assume that each of these are 1 liter containers. So if the container size is the same, we're going to see an increase in entropy as we increase the temperature. We can also look at pressure effects. So let's just assume we have 1 mole of gas in a 1 liter container at 1 atmosphere. As we increase the pressure, think about what happens to our particles. So as we increase the pressure, as that pressure comes down, the particles are going to become more compact, and they're going to be more ordered. So if we compare these two, we have 1 mole of gas, and if we have a larger entropy, the pressure needs to be smaller. So we're going to say this is 1 times 10 to the minus 2 atmospheres. So if we increase the pressure, the particles are going to become more compact. And so when we decrease the pressure, we're going to see a larger entropy change. So these are all the different effects that come up that are going to be the most common. Typically, you'll say, hey, we're comparing this and this. Which one has a larger entropy? And this would kind of be some examples of each of those effects. On Friday of last week, we defined what the first law of thermodynamics was. And the first law of thermodynamics allows us to kind of account for different energy changes, but it doesn't really say why a particular thing happens or what the driving force for a particular reaction is.